In the earliest moments of the universe's existence, it was unimaginably hot and dense. As time passed and the universe began to cool down, electrons started interacting with atomic nuclei, leading to the creation of the very first atoms. These atoms marked the beginning of a long and complex process, setting the stage for the formation of the first stars and galaxies, which appeared several 100 million years later. But how exactly did these stars and galaxies form? What forces were at work, and how did they coalesce to create the structures that fill the cosmos today? To answer these questions, scientists have been working for over 2 decades on a project that represents one of humanity's greatest technological achievements, a $10 billion time machine that promises to give us unparalleled insights into the early universe. This time machine is the James Webb Space Telescope, JWST, a device capable of looking back in time by capturing the light that has traveled for billions of years to reach us from distant galaxies and stars. Imagine for a moment that you are located 65 million light-years away from Earth, somewhere in the Virgo cluster of galaxies, and you have access to an incredibly powerful telescope. Peering through this telescope, you would not see Earth as it is today, but instead, you would witness a world ruled by dinosaurs, as the light you observe left Earth millions of years ago. This concept, of looking back in time by observing distant objects, is at the heart of how the JWST will operate. Of course, there are many technical challenges involved, but this telescope is designed to overcome them and provide us with astonishing new views of the universe. The James Webb Space Telescope is 100 times more powerful than its predecessor, the Hubble Space Telescope. One key difference is the size of their mirrors. JWST's mirror is much larger, but despite its size, it is remarkably lighter, 113 kilograms, 249 pounds, less than Hubble's mirror. This larger mirror is crucial because it allows the telescope to collect far more light, and in astronomy, the more light you gather, the clearer and more detailed the images become. The JWST's mirror is composed of 18 hexagonal segments, each measuring 1.32 meters, 4.3 feet, in diameter. These segments are designed in such a way that they can be folded up while the telescope is being launched and then unfolded once in space. Once fully deployed, the mirror's focus is fine-tuned to an incredibly precise degree, with adjustments as small as 1/10,000th the thickness of a human hair. This level of precision is necessary because the telescope will be observing extremely faint and distant objects, such as the first stars and galaxies that formed after the Big Bang. The JWST operates primarily in the infrared spectrum, which is essential because light from these ancient objects has been stretched by the expansion of the universe. This phenomenon, known as redshift, causes the light from distant galaxies to shift into the infrared part of the spectrum. By observing in infrared, the JWST can detect light that has traveled across billions of years, giving us a window into the early universe. One of the telescope's main instruments is the near-infrared camera, or NIR-CAM, which serves as the primary imaging tool. NIR-CAM is equipped with 10 detectors that are highly sensitive to infrared light, allowing it to capture images of the first stars and galaxies. In addition to this, NIR-CAM features a coronagraph, which works by blocking out the light from bright objects like stars, enabling the telescope to see much fainter objects that are normally hidden in the glare. This is similar to how you might block the sun with your hand to get a better view of something ahead. The coronagraph will be particularly useful for studying exoplanets and distant stars that are otherwise too dim to observe directly. However, NIRCam alone cannot provide all the information needed to understand distant objects fully. For instance, to determine whether an exoplanet has an atmosphere, or if it contains water, another tool is required. This is where the near-infrared spectrograph, or NIR-SPEC, comes in. NIR-SPEC analyzes the spectrum of light emitted by an object, which contains vital clues about its temperature, mass, and chemical composition. When atoms and molecules interact with light, they leave unique patterns, known as spectral lines, on the light spectrum. By studying these lines, scientists can deduce a wealth of information about the object in question. One of the challenges with observing faint, distant objects is that it can take a long time, sometimes over 100 hours of exposure, just to gather enough light for analysis. To save time and resources, NIR-SPEC is equipped with a groundbreaking feature, the ability to observe hundreds of objects simultaneously. This is made possible by its microshutter system, which consists of 250,000 tiny shutters that can open and close individually to control which objects are observed. This technology will allow the JWST to focus on multiple targets at once, greatly increasing its efficiency. The telescope also features a fine guidance sensor, FGS, that ensures it remains accurately pointed at its target throughout long observation periods. Developed by the Canadian Space Agency, the FGS plays a crucial role in stabilizing the telescope and capturing precise data. Another major instrument is MIRI, or the mid-infrared instrument, which allows the telescope to see even deeper into space. While near-infrared light can reveal a lot, there are certain regions of space, particularly those filled with thick dust clouds, where it struggles to penetrate. MIRI, which operates in a longer wavelength infrared range, is designed to look through these dense clouds, providing a clearer view of newly forming stars, distant galaxies, and even comets. However, MIRI faces its own challenges. It must be kept extremely cold, at a temperature of just 6.7 Kelvin, about 266.5 degrees Celsius, to function correctly. To achieve this, the JWST is equipped with a cryocooler, which circulates helium through the instrument to keep it cool. One of the telescope's most innovative features is its sunshield. The sunshield is crucial because the telescope must be protected from the heat of the sun, earth, and moon. This enormous shield is the size of a tennis court, composed of 5 layers of special material that effectively block out heat, allowing the telescope to remain cold enough to function properly. Each layer is made from a heat-resistant material called kapton and is coated in aluminum to reflect heat. The sunshield ensures that the telescope can maintain a stable environment, free from the interference of external heat sources. Once deployed, the JWST will travel to a special location known as Lagrange Point 2, located 1.5 million kilometers from Earth. At this point, the gravitational forces between the Earth and Sun are balanced, allowing the telescope to remain in a fixed position relative to Earth. This location is ideal for continuous observations without interference from Earth's shadow. The possibilities of the James Webb Space Telescope are truly extraordinary. Beyond studying the first stars and galaxies, it will be able to examine the atmospheres of exoplanets, potentially identifying planets that could support life. By using infrared light, the telescope can even analyze the rings around planets like Uranus and Neptune, which are difficult to observe in visible light. As we await its discoveries, the JWST stands as a testament to human curiosity and ingenuity. This incredible telescope promises to revolutionize our understanding of the universe, shedding light on questions that have puzzled scientists for centuries. From the birth of galaxies to the potential discovery of alien life, the JWST is poised to unlock the mysteries of the cosmos and bring us closer to